Hello everyone, I'm Sina Salahshour. I am a master's student studying at Toosi University of Technology with a major in Mechatronics. I want to talk about cooling heating system. First, I explain why the cooling heating system is important. Then I talk about the parts of this project, and at the end I show you the simulation and explain that in details. As you can see, 39% of the energy consumption is in buildings, 80% of that is in office, and 21% of that is in residential. Also, 31% of that is in industry, and 28% of that is in transportation. It says that most of the energy consumption is in buildings, and it's important to know about that and control it. As you can see about energy consumption of home, 31% of the energy used for space heating, 12% of that used for space cooling, and also you can see other items. And it says that, and it's clear that the most energy used for heating and cooling the space and the air. At office building, 39% of the energy used for heating, ventilation, and air conditioning, and 25% of the energy used for lighting. As you can see at the office building, most of the energy used for cooling and heating space too. Up to now, I talk about energy consumption, and we found out why a cooling heating system is important. Next, I explain parts of this project, and I talk about these parts. First, for simulating, we must know about a thermal model of the space. Inside the house, the heat is generated by the cooling heating system, people, or stuff like appliances and the other things. These heat flux could transfer outside the home through the walls, ceiling, floors, windows, and doors. Also, heat flux is outside the house could transfer into the house through these items. In this project, we just consider windows, doors, walls, and ceiling. The heat is transferred via convection, conduction, and radiation. In this project, we just consider conduction and convection because most of the heat is transferred via these items. For using convection in SimScape, you can choose convection heat transfer block. On the left side, you can see the convection equation. For using this block, you just determine the area and heat transfer coefficient. This block measures the temperature difference by itself. Using conduction in SimScape, we can choose a conductive heat transfer. On the left side, you can see the conductive equation, and for use this, we must just determine the area, thickness, and thermal conductivity. And this block measure the temperature difference by itself too. Next, I want to talk about the type of the sensor. As you can see, for measuring temperature, we have 4 types of sensor. RTD stands for Resistant Temperature Detector. RTD is a sensor which resistance changes as its temperature changes. The resistance increases as the temperature of the sensor increases. The resistance vs temperature relationship is linearly. And RTD works by using a basic principle. As the temperature of the metal increases, so does the resistance to the flow of electricity. Electrical current is passed through the sensor. The resistance element is used to measure the resistance of the current being passed through it. Second type is thermocouple. A thermocouple is a sensor that measures temperature. It consists of two different types of metal joined together at one end. When the junction of two metals is heated or cooled, a voltage is created that can be correlated back to the temperature. A thermocouple is a simple, robust, and cost-effective temperature sensor used in a wide range of temperature measurement processes. Third type is thermistor. Thermistor, derived from the term thermally sensitive resistor, are very accurate and cost-effective sensor for measuring temperature. Available in two types: NTC, negative temperature coefficient, and PTC, positive temperature coefficient. It is the NTC thermistor that is commonly used to measure temperature. They are very sensitive and react to a very small change in temperature. They are best used when a specific temperature needs to be maintained. Last type is a semiconductor. Semiconductor-based temperature sensors or integrated circuit temperature sensors operate with a reverse bias, have a small capacitance, and a low leakage current. They commonly use a band gap element which measures variations in a forward voltage of a diode to determine temperature. To achieve reasonable accuracy, they are calibrated at a single temperature point. For measuring the temperature of the space, commonly use thermistor type because of its accuracy and cost-effective performance. It has a different type and shape, as you can see on the left side. Based on your usage, you can choose one of them. As you can see on the right side, by changing the resistance at the interface, the voltage would be changed and you can measure the temperature. For measuring temperature, you can use a wireless type or wire type of sensor. Each of them has its disadvantages or advantages. For wireless type, for example, you don't need to wiring, but it's expensive. But for wire type, it's cheaper than the wireless, but you need to wiring. And based on your usage or budget, you can choose one of them. Choosing the sensor, we must consider some items. One of them is range. Range of the sensor must cover the operation range, because if it would be lower than the operation range, we can't control precisely. And if it would be higher than the operation range, it costs extra money. The next item is accuracy. It must have appropriate accuracy so we can control the system precisely. Based on our usage, it must have a appropriate resolution because we can detect the small changes. The last item is drift. Because we use the system for years, it must have a low drift so we can control well. In SimScape, we use temperature sensor block. I can't find those type of sensor, but this block measure the temperature well, and just we must determine the thermal reference, and it measure the temperature by itself. The next item is actuator. In cooling heating system, the heater, the cooler, the fan, the radiator, and stuff like that are an actuator. They have different types, and based on our usage and budget, we can use one of them. The project that used SimScape for simulating the cooling heating system that I've seen, they use control heat flow rate source block for generate the heat, and we must use a signal, and based on that signal it produce the energy and heat. It's precise and useful. Next part is a control system. In this part, after sense the temperature, if temperature is higher than a specific value, the cooler must be turned on, and if lower than a specific value, the heater must be turned on. For a specific range, actuator doesn't do anything, and in this part we use simulating for control system. Now first I explain why the cooling heating system is important. After that I explain a little about the parts of the project, and next I wanna show you the simulation and talk about that in SimScape. Now I wanna talk about the simulation file and explain it. It consists of three parts, as I mentioned, the thermal model and the actuator and control model. Now I explain the thermal model. At this part we have convective heat transfer and conductive heat transfer. For conductive we must determine the thermal mass. As you can see, we have 4 walls, window, door and ceiling. For each of them we must determine the parameters, and now I want to show you these parameters. The window, we have for 2 walls we have 4 windows, and this is the sum of the windows mass. The wall number 1, number 2, they are the same. Window and ceiling. And for conductive we have these: the area, thickness and thermal conductivity. We have 4 doors for them, and that is the sum of doors area. The window, the wall, window and ceiling. For convective we have these: window, wall, window and ceiling. They are the same, so that I don't show them again. That is the air thermal mass. This part for the heat that is generated by the human. Each human produce and generate 100 watts, and we consider that we have 20 people in this space. We can show. In this part we have a sensor. As I mentioned, we must consider the thermal reference, and for showing the measurement we must use the physical to simulating converter, and we must determine the unit that we choose a Kelvin. Now I want to talk about the external temperature. For producing the external temperature we use a control temperature source, and for producing, we use the signal. We determine the temperature like that. We have 4 days, 12 of them for cold day and 12 of them for a hot day. For use signal, we must use the simulink to physical converter. To solve and run, we must use a solver configuration. Now I wanna explain the actuator and control part. For generating heat, as I mentioned, we use the controlled heat flow rate source. For this, we must use a simulink to a physical converter. We have two parts, cooler and heater, that each one producing the signal to generate the heat. First, we talk about the cooler. At this part, it decides to turn on or turn off the cooler. If the temperature is higher than 298 Kelvin, the cooler would be turned on, and if the temperature is lower than the 295 Kelvin, the cooler would be turned off. The generated heat increase by 1 watt each time step, as you can see in there. This part determines the upper limit of the generated heat. At this part, if the temperature is higher than 299, the upper limit is 3000 watts, and if it's lower than 299, the upper limit is 2500 watts. At this part, if the cooler would be turned off, the generated heat decreases slowly by this. Now I wanna explain the heater. It works like a cooler, but if the temperature is higher than 293, the heater would be turned off, and if it is lower than 291, the heater would be turned on. And about the upper limit, we have this. If the temperature is lower than higher than the 289 Kelvin, the upper limit is 1500, and if the temperature is lower than 289 Kelvin, the upper limit is 2000. At this part, like a cooler, if the heater would be turned off, if the generated heat decreases slowly because of this. Now I wanna run a little file for different types. First, we don't consider the control and actuator system. For that, we choose this. Now we choose the cold day 1 and run. Now we have the external temperature variation. This is the temperature variation during the day. The temperature average is 291.9. Now I wanna see the temperature variation of the space. Because of the generated heat of a human, the temperature variation was good and it's not so cold. Now we consider the actuator and control system and run. As you can see, the temperature average increased a little bit, and it is 292.1, and the temperature variation of the space is like this. At this part it shows that the heater turned on. Now I want to see when the heater is on exactly. At this during time the heater is on. Now we choose the cold day 2, and we don't consider the control and generated heat, and run. As you can see, the temperature average is 290.2, and the temperature variation of the space is like that. As you can see, the temperature goes lower than the 291. The variation of external temperature is like this, and it's clear that it's cooler than the other day. Now we consider the control and actuator part, and run. As you can see, the temperature average is 292.7. The temperature is increased. The temperature variation of the space like this, and you can see at this time the heater would be turned on. And now I want to see when the heater is working exactly. You can see during this time the heater is on. Now I choose the hot day and hot day 1. Now I don't consider the actuator and control system, and run. The temperature average is 302.2. that is higher than the specific value that we determined for upper limit for the temperature. We determined 298 Kelvin for upper limit of temperature. The temperature variation is this for of the space, and for external temperature variation we have this. Now I consider the actuator and control, and run. The temperature average is 296.5, and the temperature variation of the space like this. Now I want to see when the cooler is on. You can see during these times the cooler is on. Now I choose the hot day 2, and I don't consider the actuator and control system. and run. The temperature value is 301. As you can see, that is higher than a specific value that we determined for the upper limit of the temperature. The temperature variation of space, like these, and the external temperature variation, like this. Now I consider the actuator and control part and run. As you can see, the temperature average is 296.3, and the temperature variation of the space, like this. At this time and this time, the cooler would be turned on. Now I want to see when the cooler is on exactly. As you can see, during these times the cooler is on. Start time of the simulation is 86,400 seconds. That means 1 day. I want to talk about another simulation file that we just changed the actuator and we use DC motors and the fan. We have 6 DC motors that when the temperature goes upper than 298 Kelvin, the motor is on, and when it goes lower than the 295 Kelvin, the motor is off. And we have 6 fans that pass on the cold air to the space. At this part, when the temperature goes higher than the 299 Kelvin, it passes on the 275 Kelvin air, and if it goes lower than 296, pass on the 285 Kelvin air to the space. So we run. Now I want to see the temperature variation. At this time, the fan passes on the 285 Kelvin air, and that this time it passes on and the 275 Kelvin air to the space. Now I want to see when the fan is working. As you can see, after this time the fan is on. This is the external temperature. Thank you for watching this video.